So we're happy to have Alex Ortiz today, and he's going to tell us about tangency counting for well-spaced circles. Take it away, Alex.
Cool. So yeah, thank you to Joris and the organizers for inviting me to give a talk. So yeah, I'm going to be talking about a project that's so the title of the talk is the same as the title of the paper. This is based on joint work with Dominique Maldague, um, and this is about a problem about counting tangencies for circles. So I'll just start by kind of giving background on the problem and explaining a little bit of its history, and then I'll talk about where does the well-spaced come from and what did we do. Cool. So first, let me just sort of introduce this Kakea type problem for circles. So uh, the two groups, Besekovich-Rado and Kinney, they independently were studying sets in the plane that have a circle of every radius. And they showed that if a set has a circle of every radius in the interval from 1, 2, you can make those really small. So you can make these have measure 0. So this picture shows the first few iterations of a Perron tree type construction of a set of a thin set of circles. So this particular recipe comes from Kolasa and Wolff. Cool. So we call a compact set in the plane that has a circle of every radius in the interval from 1 to 2. We call that a BRK set. And and Tom Wolff proved that every BRK set has dimension 2. And he did that. He actually gave two proofs of that. And one proof uses a bound for a delta discretized circle tangency problem. So now I'm going to describe a few different discrete circle tangency problems, and one of them is the problem that Wolff was studying. Okay, so here's the first version of the problem. It's just about counting pairs of tangent circles. So if I have a set of circles in the plane and I stipulate that no three of them are tangent at a point, the question is to count the number of pairs that can be internally tangent at a point. Okay, and the assumption that no three are tangent at a point is to rule out what's called the clamshell. So if I put all the circles in this kind of configuration that looks like a clamshell, and I put say n circles all like that, uh, n circles in a clamshell, this is going to have the maximum number of pairs that are tangent. So basically every pair is tangent. So to get some, non-trivial sort of interesting bounds, we have to add some condition that rules out a big clamshell. So this is the first version of the problem. And a slightly different version of the problem, but really closely related, is instead of counting pairs of circles that are tangent, instead we can count how many places are there where there is a tangency. So this is like a very similar version of the other problem. And in this version, we don't have to add the assumption that circles aren't, that we don't have to rule out clamshells. Okay. And then yet a third version of the problem will introduce a small scale delta, and we will count what are called two-rich tangency rectangles. So a tangency rectangle will be one of these delta by root delta rectangles, uh, which is tangent to two or more circles. And the scale root delta, that's chosen so that if these circles have radius about 1, then their 10 delta neighborhood is going to contain the tangency rectangle completely. So this is like an appropriate way to kind of blur out the second version of the problem. And Wolff proved a bound for this problem. So here's Wolff's estimate for tangency rectangles. So the theorem says that if I have a set C1 of circles whose say n circles in the plane and their radii are pinched between 1/2 and 1, and I have a set C2 of circles with radii pinched in the interval from 3/2 to 2, then Wolff showed that there's at most n to the 3/2 plus epsilon many two-rich tangency rectangles. One of them where the tangency rectangles are tangent to at least one circle of C1 and at least one circle of C2. Okay, so this kind of separation hypothesis was important, and it's not possible to get this kind of bound without some sort of separation assumption on the circles. So Wolff proved this particular theorem because he was motivated by the local smoothing conjecture for solutions of the wave equation in R2, which roughly says that even though a solution to the wave equation, so the second derivative of u equals the Laplacian of u, even though those solutions can focus into and make spiky peaks at any fixed time, they can't do that, and they can't sustain a focused spiky peak over an interval of time. So he studied the local smoothing conjecture by thinking about the wave packets of a solution. And the geometry of those wave packets is closely related to the geometry of tangency rectangles. Okay, so now I'll say a little bit more about wave packets of a solution to the wave equation. So we're going to let gamma be this set in R3. It's the piece of the light cone between at height between 1 and 2. And then from Fourier restriction theory, if we consider this Fourier extension operator applied to a function f, which is essentially the Fourier transform of a function that's supported on this gamma, then that's a solution of the wave equation. And it has its Fourier transform supported in gamma. So to make the wave packet decomposition of this solution, what we do is we take the 1 over r neighborhood of the cone and we divide it into these boxes. So this is a picture I took at MIT a few years ago of a planter that I think it was like in February or something. So there wasn't anything growing in the planter. But it's a really nice planter. It shows exactly the wave packet decomposition of the cone. And so then we define E of f theta to be the E of f restricted to one of those boxes. Cool. So since those boxes are disjoint, the EF thetas are orthogonal in L2, but they're also orthogonal in LP when P is bigger than 2 in a certain sense. And this was what Wolff was interested in. So he proved the first, what we now know as decoupling inequalities for the cone. So here's the Sharp theorem due to Bourgain and Demeter, which says that if we take our solution of the wave equation and we consider its wave packet decomposition, then we have an orthogonality in LP. Okay, and there's two different ranges of P here, one for small values of P and one for large values of P. And then there's some powers of R. And those powers of R are what we get by interpolating the bound at P equals 6. That's the critical bound with P equals 2 and P equals infinity. So Wolff used that tangency rectangle theorem that we looked at, and he proved the same bound in the second block for values of P bigger than 74. And that implies the Sharp local smoothing estimate when P is equal to 74. Cool. Okay, but to say a little bit more about so the discrete and continuous problems. So in the early 90s, these 5 authors, Clarkson, Edelsbrunner, Guibas, Scherer, and Welzel, they introduced this method of cuttings in computational geometry. And this is kind of like a forerunner of the polynomial method. So they proved new bounds for a number of incidence geometry problems, and they also reproved some old bounds, like the Semerity-Trotter theorem, but they got a good implicit constant. I think like an implicit constant of 10 or so. And Wolff was really interested in that. And in his survey on Kakea from '99, he wrote about each of these tangency counting problems. and he also wrote about the continuum problems like local smoothing and the BRK set problem. And he was motivated by, how much does the discrete problem tell us about the continuum problem? Is it just a matter of, is it a straightforward adaptation, or is there really something new that happens when you look at the continuous problem? So now let me say what I think is fair to call Wolff's tangency counting problem, what that is. So if we have n circles in the plane and no three of them are tangent at a point, we want to count the number of pairs so that Ci is tangent to Cj. So we'll write this symbol Ci tangent Cj when that happens, and then we'll let this fancy I be the pairs that are tangent. The goal is to count that. And because no three are tangent at a point, we rule out the clamshell configuration, and we expect to get something better than n squared. Okay. So let's talk about sort of a first observation we can make about the problem. This is what Wolff called the easy bound. So if we have three circles in the plane, so those are pictured like these blue circles here, then there are at most two other circles which can be tangent to those three circles. So those are pictured in red and orange here. Okay, so when we let I be the set of pairs that Ci and Cj are tangent, we can make an n by n incidence matrix. Aij is 1 when we have a tangency, and it's 0 if they're not tangent. So by this circles of Apollonius observation, there's no 3 by 3 submatrix of ones. And so by a theorem from graph theory, that means that the number of circle tangencies is no more than n to the 5/3. Okay, it's natural to wonder about, trying to do better and also wondering about how sharp that is. But before thinking about that, it's helpful to think about the problem from another perspective. So this is what I call the dual perspective, what Wolff also called the dual perspective. So we say that we're thinking about two circles that are tangent, and they have centers and radii. The centers are going to be points x, y, and r2, and the radii are numbers r and s. And those circles are tangent exactly when this quadratic equation, delta of xr and ys, is 0. And geometrically, that means that these points lie on a light ray. So this could be like the point xr, and that could be like the point ys. And so another way to think about the tangency counting problem is we want to count, if we have a set of points in R3, we want to count the number of pairs where delta of xr and ys is 0. So shifting it to a problem about this quadratic constraint between the points in R3. And Wolff brought this up because there's a direct analogy between this problem and the Erdős unit distance problem. So the unit distance problem is a very similar kind of question about points in R3. It asks for, if I have a set of n points, how many of those could be at a unit distance from each other? Okay, so very analogous problems, and I think that Wolff imagined that they were very similar too. And importantly, the method of cuttings that I mentioned earlier, it applies to both of these problems, and it gives a bound for both of them. So Clarkson, Edelsbrunner, Guibisch, Scherrer, and Welzel, they used cuttings, and they showed that a set of n points has at most n to the 3/2 many unit distance pairs. And then regarding sharpness, Erdős showed that if you take a grid of points, then the most popular distance happens at least n to the 4/3 log n many times. So there's a gap there between 3/2 and 4/3. And then that bound n to the 3/2 held for quite a long time. And then in 2017, Joshua Zahl showed that the number of unit distances is at most n to the 3/2 minus a little bit. And he used tools from real algebraic geometry and together with the polynomial method. Okay, but those 5 authors, Clarkson et al., they weren't studying the circle tangency problem, but so Wolff was the first one to observe that the cuttings method applies equally well to the circle tangency counting problem. So he also showed that there's n to the 3 halves many circle tangencies. And then Ellenberg, Solymosi, and Zahl showed in 2016 that they removed the epsilon. So they took off the epsilon in the tangency counting problem. And then moreover, they showed that the n to the 3 halves bound is sharp if we're looking at circles in a finite field. So in this example, they take all the unit circles in FP2. And then the number of circles is p squared, and then they showed that the number of tangencies is about p cubed. So then we have n to the 3 halves many. So then n to the 3 halves is the right bound in that case. And that means that if we want to break the 3 halves barrier on this problem, we have to actually distinguish R from finite fields somehow. Okay. So here's an example which shows how small we can expect the tangency counting bound should be. It's also a grid, so we're going to take the set of circles to be in this grid configuration. So there's just I just showed a few. I showed a grid in this picture, and then each dot corresponds to a circle downstairs. But I didn't visualize all the circles, just the ones that are highlighted here. Otherwise, it'd be kind of a messy picture to see. Okay, so I wanted to kind of give a heuristic for why 4/3 is the right bound for the circle tangency counting problem in this case. So we want to count the number of points in this lattice that are separated by a light ray, and the lattice looks the same in all directions. So it suffices to count how many points are tangent to 0, 0, 0. Okay, and then when we phrase that in terms of delta, it means that the set we're looking at is really Pythagorean triples. So n3 squared is n1 squared plus n2 squared. So we could open a number theory book and we could just see how many of those there are for numbers in the range from 0 to m. And we can also give kind of a heuristic based on probability. Okay, so the number of tangencies in this set overall is like the number of points that we have times the number of tangencies at 0, going off of the way that this set kind of looks the same in every direction. So we just have to count these tangencies at 0. So each of these numbers, n3 squared and n1 squared plus n2 squared, those are about size of m squared. So if these were random and we were just counting collisions, probabilistically, then the probability that these two numbers would collide is just about 1 over m squared. Okay, so then since there's m cubed many triples, the expected number of collisions would be about m cubed times the probability. So we expect about m many points to be tangent to 0. Okay, so then that tells us that we expect the number of tangencies overall to be about m cubed times m, and then sure enough, that's n to the 4/3. Okay, so yeah, so if we do this a little bit more carefully, then this example has at least n to the 4/3 log n many tangencies. So n to the 4/3 is basically the right thing to shoot for. Cool. So here's the conjecture then, and Wolff made this conjecture in that same survey on Kakea. If we have n circles and no 3 are tangent at a point, then at most n to the 4/3 plus epsilon many pairs are internally tangent. Cool. So here's what Dominique and I did. So we have a new bound for the number of tangencies for a well-spaced set of circles. So let me say what a well-spaced set is first. So if we're talking about a set in a unit cube, we say it's well-spaced if there's some number rho so that E is rho separated and it has essentially maximal cardinality with that constraint. So cardinality about rho to the -3. So these are going to be things that are like perturbations of a grid, although they don't have to be grid-like in any real sense. Okay, so then we'll say a set of circles is well spaced if the set of its center radius pairs is well spaced. Okay, so then here's our theorem. So for every well-spaced set of n circles that has center radius pairs in this unit cube, and no three of them are tangent at a point, there's at most n to the 25/18th many internally tangent pairs. So that's coming a little bit closer to this 4/3, but it still doesn't actually attain the 4/3 bound. And the key input to this is it's a new sharp bound for the number of tangency rectangles for a well-spaced set of circles. Okay, so let me the problem that we're talking about is this version of the tangency counting problem. If instead we shift the focus to counting tangency rectangles, then we proved a sharp bound for the number of rich tangency rectangles. And so now I'm going to shift the problem over to the dual perspective, and then for the remainder of the talk, we'll just be thinking in terms of the dual perspective. Okay, so the analog of a tangency rectangle is going to be what we'll call a light plank. So a delta by root delta by one box that's tangent to a light cone, we're going to call that a light plank. And then this is the picture to have in mind. So downstairs, there's going to be a delta by root delta rectangle. And then imagine a light ray coming out of this rectangle parallel to the short side. Then a light plank would be something like this. Okay, so the dimensions of this box are going to be 1 on the long side, delta on the short side, and then root delta on this medium side. Okay. And then this is tangent to the cone, so there's a circle here, and then this plank is tangent to this cone. So here's another picture of that. So there's 5 circles in this picture, and then they have 5 corresponding dual points. So and then there's 2 tangency rectangles pictured in pink, and then there's corresponding orange light planks that are too rich in the points. Okay, so instead of counting tangency rectangles, we're gonna just think about counting light planks. Cool. So here's the bound that we have for rich light planks, and this bound is sharp. So what we showed is that the number of delta by root delta by 1 light planks, which are too rich for a set of well-spaced circles. So here I've stated the version of the theorem where we have delta to the half separation. We have at most n to the 4/3 many too rich light planks. And then we could also count light planks that have more than 2 points in them, and then the bound scales like n to the 4/3 over mu to the 4/3. Okay, and this bound is sharp because we can make a random set of well-spaced circles which obeys that the number of light planks that are O of 1 rich is about n to the 4/3 plus epsilon. So that's the sense in which the bound is sharp. Okay. So now let me show you how we get the 25/18 bound using the estimate for tangency rectangles like a black box. So the observation to make is that every pair of tangent circles they are tangent also themselves to some tangency rectangle. So that's tangent. Every pair, is tangent to some tangency rectangle. And we're going to choose the scales. So I'm going to so these are going to be, let me say the scales after I talk about light planks. And so equivalently, light planks, so these are going to be n to the minus 2/3 by n to the minus 1/3 by 1 light planks. And what we'll do is we'll pigeonhole so that every light plank has about the same number of points. So pigeonhole, so every plank P is mu rich. Cool. So then the number of tangent pairs is we can use a union bound. So we can sum over all these planks, and we can just count the number of pairs that are tangent, but where both of the circles, their center radius pairs are in this plank. Okay, and now the set of circles that's in a plank is not well spaced in the sense of our theorem, so we just have to rely on Wolff's bound. Okay, so the number of circles in a plank is mu, so then this is at most the number of planks times mu to the 3/2. So we'll just reuse the 3/2 bound. Okay, and then we use our black box that the number of planks is at most mu to the minus 4/3 times n to the 4/3. Okay, and then this power of mu is 1/6. All right, and then finally by well spaced, the number of points in a light plank that's at most 1 over the separation. Okay, so these are n well-spaced points. They're n to the minus 1/3 separated, and so there's at most n to the 1/3 points in there. Okay, so then our final bound is n to the 4/3 plus 1/18, and that's the 25 over 18. Okay, so really the main technical component of the project was the estimate for tangency rectangles, and then for the rest of the talk I'll be describing what we did for that problem. Okay, so we really want to count rich light planks, and then here is the setup. So we have mu rich delta by root delta by 1 light planks for a set of n, which is delta to the minus 3/2 many points. They are root delta separated, and the center radius pairs are in this unit cube. So I'm going to just scale the whole picture up. So we're going to let R be 1 over delta and scale everything up, and now we'll just have a rescaled version of the problem. And after we do that, we're going to have a set of R to the 3/2 many R to the half spaced points, or equivalently, we'll think about them like unit balls. And then P is a set of mu rich planks. And one of the original delta by root delta rectangles, it corresponds to a 1 by R to the half by R light plank. And then the goal is just to get this 4/3 bound. So mu to the 4/3 times P is smaller than x to the 4/3. Okay, and this scaling is a little bit more friendly for thinking about restriction theory. So essentially our approach is the high-low method. So we define this function, which is the overlap or multiplicity function of the planks. So the notation is kind of chosen suggestively. So we have, it looks like indicator function of P, and for the talk, you might as well think about it like the indicator function of P. But instead it's going to be a smooth version of that, which has a proper Fourier support, and it's going to have a Schwartz tail. But for the sake of the talk, we can just ignore those details. And each of the planks that we're summing over is mu rich. So if we define the incidences between the unit balls and the planks, that's the integral of f over x, and that's at least mu times p. And this is the setup for the high-low method. Okay, so that means that we're going to be thinking about the Fourier transform of f of x. So each of these indicator functions of a plank is Fourier supported in a dual plank of dimensions 1 by r to the minus half by r inverse. And as the directions of those planks changes, then the direction of the dual plank also changes. Okay, so let me draw a picture of a few planks. So here's kind of like a front view of a set of planks that has this property. These are their dual planks. Okay, so all of these contain the origin. And then the high frequency part is just the part of these planks that has magnitude about 1 in the x3 direction. Okay, so this is the C3 axis. And this is what we'll call the high frequency part. So the part of the Fourier support in this region. So that part is actually Fourier supported in this neighborhood, 1 over R neighborhood of the cone. Okay, and then we have all the other frequencies too. So the full Fourier transform is a sum over dyadic k, where the value of xi is about 1 over k. The high frequency part is where k is about 1. And then the very low frequency part is when xi is smaller than r to the minus half. So in the picture, I should have highlighted that too. So in the picture, this part is where xi is smaller than r to the minus half. And then there's no cone structure to exploit really. So we'll just have to keep that in mind. Cool. But the positive feature about the high part is that we can apply decoupling theorems to it because of its nice Fourier support. So we can think about this in cases. So if the high frequency part dominates the incidences, then we'll just be thinking about that function and we'll be trying to exploit its Fourier support. So suppose by pigeonholing that every point of x is contained in about r many wave packets of the function f. So then if we double count the incidences, we get this relationship between that parameter r and the number and the richness mu. Okay. And decoupling with the sharp exponent of 6, it's a bound for the integral of this function to the 6th power on x. So now let me state the version of refined decoupling that we prove, and then I'll state another version that we'll use in this sketch of the proof. Okay, so here's the refined decoupling theorem that for the cone that we prove. It's stated in terms of a square function. Okay, so the setup is the exact same as what we're thinking about. We divide the function into wave packets, and then the key is that we can restrict to a level set of this square function of f. So the square function of f doesn't have any oscillation. That's like a purely, it just has the information about the overlaps of the wave packets. So this is the precise form of the decoupling theorem that we use, and I'll say something more about it at the end. But I want to kind of pivot and then state a version of refined decoupling that's a little bit more geometric and a little bit more familiar. So we say that one of these wave packets, like a function fp, it's micro-localized to the pair p and theta if p is a light plank, which is dual to this particular cap theta in the neighborhood of the cone. And then fp is concentrated in p, so rapidly decaying away from p. And for the sake of the talk, you should just pretend that there are no Schwarzschild and f is just supported in p and its Fourier transform is supported in theta. Okay. So this is the version of refined decoupling which comes from this 6-author paper where they were investigating restricted projections to lines. Okay, so suppose we have a function f, which is a sum over planks of these wave packets. Each one is micro-localized to some pair, and each one has amplitude about 1. So like they're the characteristic functions of the planks. If x is a union of unit balls, and every point in x is contained in about r of the planks p, then we get this bound for the L6 norm. So we get something that, so it separates out the contributions from the individual wave packets, and we also get this gain of r over the number of planks. And as long as r is a lot smaller than the number of planks, that's going to be a big gain that we're going to exploit. Okay, so that exact statement of refined decoupling applies verbatim here. So we can just plug it in and just kind of walk through the algebra to see what we get as a bound. Okay, so plugging in that bound, we get this estimate for r to the 6 times x, and each plank is a 1 by r to the half by r object. So the L6 norm is just the volume of one of those planks to the 1 over 6. Okay, so in particular, the L6 norm to the 6th power is r to the 3 halves. All right, so let's just plug that in and then just step through what we get. So plugging that in and then canceling out all the like powers of r on both sides, we get this inequality that's kind of reminiscent of like an L4 inequality almost. And then we plug in the double counting inequality. We think about it like a lower bound for r, and it tells us that mu to the 4th times the number of planks cubed is smaller than x cubed times r to the 3 halves. Um, and and this argument so far hasn't used well spaced at all, actually. But now we will use the assumption that x is well spaced. So because of the scaling, the size of x is actually about r to the 3 halves. And so when we plug that in, we get, and then we take the cube root, we recover this 4/3 tangency bound that we were looking for. So the high frequency case, it really only used actually the cardinality of x and didn't actually use the well-spaced assumption at all. So the well-spaced actually it actually comes in when we think about smaller frequencies. So let me say a little bit about that and then talk about what properties of the lower frequency functions we're going to use. So let's make a notation that f sim 1 over k is the frequency projection where C3 is pinched between 1 over k and 2 over k. Okay, and then we'll make a new notation for a rescaled version of r. So r sub k is k to the minus 2 times r. So there's really two properties of this function that we can use. So the first is its frequency support. So if k is a lot smaller than r to the half, then this function, its Fourier support, that's contained in the 1 over k dilation of a rk inverse neighborhood of gamma. So the way that I think about it is that when k is much smaller than r to the half, we have a cone structure. Okay, so once we have cone structure, we're kind of hoping that we can use some decoupling in that case. All right, and then the other property about this function that we might want to use is the locally constant property. So by the uncertainty principle, f sim 1 over k is basically constant on balls of radius k. And we're going to use, and then when we exploit, so the way that we're going to exploit that is we'll use well-spaced actually in that case. So okay, so like we said, if k is much smaller than r to the half, we're going to try to use a refined decoupling with this cone structure of the Fourier support. And then that leaves the lowest frequency case, when the incidences are bounded by the part that has no cone structure. So for that part, we don't get to use decoupling. We have to have a different kind of direct argument. So I'll walk through that now. So what do we do in the lowest frequency case? Okay, so remember by the way we define these incidences, every plank in P is mu rich. So we have mu times the number of planks is bounded by the integral of f with frequencies smaller than r to the minus half. And then the way I want to think about that is just purely heuristically. I want to imagine replacing this Fourier projection with just blur out my function at scale r to the half. And then we'll just work under the assumption, pretend there's no oscillation or tails, and just see what we get. And then morally, that's the right thing to do anyway. Okay, so every one of these planks, it's contained in a tube. So what I wrote here, a light tube. So every plank is kind of comfortably sitting in a tube where the radius of the tube is r to the half. Okay, so when we actually compute this convolution, we're just blurring out the plank at scale r to the half. And so we're really getting something which is some amplitude on this light tube. And the amplitude just depends on how much of the plank is actually in a ball of radius r to the half. And that's where this particular coefficient 1 over r to the half comes from. Okay. And since x is well spaced, I can't actually fit too many points of x inside this light tube. The maximum number of points I can fit in one of those is just r to the half, because it's r to the half separated. So that means that when I do this integral at the top, for every plank, I get a contribution of at most r to the half over r to the half. So the number of planks just cancels from both sides. It just tells me that actually the richness of my planks had to be at most 1. Okay, so, and the planks themselves, they are, so the planks P they're essentially distinct. So planks are essentially distinct. And so we can actually count how many of those there could be just maximum. It's at most r squared. So just taking into account the angle separation, there's at most r to the half many directions, and for each direction, there's r to the 3/2 many planks that fit in the ball of radius r. But then, okay, so that's actually just the same thing as the size of x, r to the 3/2 to the 4/3. So in this lowest frequency case, the bound just kind of comes for free after we apply well spaced. So let me just finish by saying a little bit about intermediate frequencies without going into the details of it too much. So the way that I described it, it seems like we could just try to bound each f1 over k, just bound each one of those separately and just add up all the contributions. But so we found that in practice, that doesn't really work that well. There's some problems when we try to make that strategy work out. So what we do instead, and this is one of the new things in our argument, is we find the dominant frequency component with a stopping time argument. So what we're going to do is the following. So by the way we set things up, the Fourier transform of f is contained in a ball of radius 2. So f itself is essentially the same thing as this Fourier projection to frequencies smaller than 1. So what we're going to do is we're going to fix every x pointwise, and we're going to compare the size of f itself to its frequency projection to frequencies just a little bit smaller. And we're going to compare those numbers, and if they're about the same, then we're going to shrink the frequency scale again, and we're going to keep going. So we're going to gradually shrink the frequency scale, and we're going to keep going as long as the size doesn't drop too much. But the moment that we see a sudden drop, we're going to declare that exponent k to be the stopping time. And on the physical side, I have a picture for how you can think about it. Geometrically, this is capturing the first time that the local behavior of f, it goes from being dense to sparse. Okay, so here is a visual, lovingly drawn out of what the stopping time kind of looks like. Okay, so so on the left, we're comparing essentially the average of f at a point x, which is the center of this ball, on a ball of radius k, to the average of f on a larger ball, okay, of radius r to the epsilon k. And f itself is the sum of these green and blue planks. And these tubes that I've drawn are just there to kind of sort of organize the planks. Okay, so between scales k and r to the epsilon k, the value of the average didn't drop too much. So we keep going. But after we zoomed out, we see that the portion of f in the ball of radius r to the 2 epsilon k, it's just a very thin portion of the ball. And so actually the average on that ball is way smaller than the average on the ball of radius r to the epsilon k. So at that point, we're going to stop and we're going to say that's the dominant frequency contribution. Okay, So we have to set this all up carefully. In particular, we have to make sure that these frequency projections that we define, they're all non-negative. The original function f is also non-negative. And so that means that at the stopping time, what we are looking at is the frequency projection to scales about r to the minus k epsilon. It's the same, okay, by definition, it's just this difference of frequency projections between these adjacent scales. But then at the stopping time, the frequency projection to this scale is basically negligible. And because these are all non-negative, that means that this piece is a lot smaller than this piece. And so the actual, okay, so that means that this frequency projection to this scale is also positive. And actually exploiting that positivity is really crucial for applying this specific form of the refined decoupling theorem that's stated in terms of the square function. Okay, so I think that's all I wanted to say about intermediate frequencies. So I'll stop there and thank you for your attention.
Thank you for a great talk. Let's thank Alex.